This machine is absolutely fantastic. And the big part is to have worked on it from sketchpad to launchpad was the experience of my life. I never told anybody this, but the last 2 years I would have worked for free because I had the honor of starting it in 1969, and like 79, 80, a year or two before it flew, I would have worked for free because I was going to see something from beginning to end. And it was each one of the phases, so I'm going to talk to you a little bit about each one of the phases and how important that is and how they're all different. I've introduced the panel. The way we're going to do it is each one of us are going to speak for 30 minutes, and we're going to get a flag over here when we get close to it, and we'll have 30 minutes for Q&A. Now then, if there's something that you think's more appropriate that you have to ask during the presentation, do it, okay? And we'll stay within our allotted time, though. There are 5 things that I want to leave with you from my experience. Political systems engineering is important. Now then, I said that last year. I had the honor of being here. And we saw all these constellation schedules and Aries and all this kind of stuff. And I said, that's all really good, guys. I said, but be aware, you know, things are going to change because they've changed from each one of the programs, and I'll show you how that's happened. And lo and behold, you know, I don't want to say I told you so, but it did. But it will continue to change. So just don't get too down or anything like that. This is just part of the business. Then I'll talk about each one of these 5 things. Freezing the configuration, but not the program plan. Simple interfaces really simplify the program. Better's enemy of good, and operational flexibilities covers a lot of shortfalls. Now I'm going to talk about each one of these things. In the development, transitioning from Apollo to ERA, there was a huge difference in technology. Apollo had, the thing is, we just didn't even know what we didn't know in Apollo. We hadn't even put a man in space. I mean, Shepard had gone up and touched the edge of space when Kennedy said, we're going to do it, you know. So there was so many, we had propulsion systems, guidance and control systems. We didn't know if people could live in space. We didn't know how to rendezvous and dock in space. We didn't know dip, okay? But we said, we think we can do it, and we did it. So, but there was huge technology difference. In the early shuttle program, we looked at a lot of different configurations. We froze those configurations early in the program, and then we stepped into, okay, how do we make this better by simplifying the interfaces and moving into operations. In the political and the program management, the political environment changed a whole lot. There was not, and this was living in the glory days. I mean, we didn't have oversight and a lot of bureaucracy. It was just go get the job done. We had a lot of support at all levels, and that made the job, I don't think we'd have gotten there, okay, with all the challenges we had if we hadn't had that environment to work in. As we moved into shuttle, the technology issues decreased, okay, but the other things continued to increase. And there's another thing that we had to do in shuttle. We had to keep the program sold. Apollo was sold, yeah, I guess it was, you know, it was sold to the president. Really asked, can we do it? And then NASA says, yeah, we think we can do it. It's going to be high risk. And he said, go do it. Well, that was the end of the selling program. But now shuttle came along. It was the continuous selling to convince the administration and the Congress and the public that it was worth doing. This doesn't sound like engineering, but let me tell you what. If you don't do it, if the engineering group and the management doesn't do it, it's not going to get done. As I said, the president was in full support in Apollo. We did it. We sold it to the White House. We had fragmented political support in the shuttle program, and it was a tight schedule. We had a lot of variability in the budget, and we had a whole lot more bureaucracy. This not having that would let the Apollo program focus on what they were doing on the technology. I think I mentioned the shuttle, the major development there, the whole list in Apollo was so great, it was unbelievable. Literally, we didn't know what we didn't know, which was good. In shuttle, we had some major developments. In propulsion systems was a major development, especially with the SSMEs and a lot of stuff. And Jody will talk about that. Thermal protection system, fully reusable. Apollo was throwaway. We used it one time, so that was a big technology issue. The avionics was big, and the reusability of the vehicle. Those were our four major technology challenges. The rest of it, we pretty well knew, okay? But then we had to balance it between something that's a single event and go into something that's routine ops. And then John O'Neill will talk more about that. Not an issue in keeping the program sold in Apollo shuttle. It was a continuous challenge. The thing that one of the big differences in between Apollo and shuttle was Apollo had things happening all the time. I mean, there were launches and there were failures and there were events. The public could see it. It was exciting to everybody. In shuttle, this thing drug along for a long time. I mean, we in the program felt great about it because we were making a lot of progress. We were having design reviews and, you know, things were coming about. We were doing subsystem tests and they were working well. But nobody saw that it wasn't exciting. We didn't have any gee whiz. Until 78, I think, is when we did the approach and landing test. Is that right, John? About 78? Yeah. That was a gee whiz. Okay, that was not in the program initially, but when we saw that orbiter on the back of the 747, it was a good engineering management test objective, but the biggest thing was it was a visible thing that got the excitement. The next step in the shuttle program, it was about to get canceled, literally. We were right on the verge of that program dying. But when that happened, all of a sudden was, get that thing in space. So that's, as a matter of fact, that's what John Yardley said, get that son of a bitch in space, you know. He says, I want that to go. And so that was what our mission was. We had to get that sucker up there. So from that point on, there were a few technology issues, but we overcame those. We had to replan every single year in the shuttle program. We never had the budget. You know, it slipped out. It began in, we started DDT&E on the shuttle program in 1972. We flew it in 81, so it was roughly 9 years it took us. We could have gotten there faster, but we had to replan every single year. Extremely frustrating. I thought it was the most frustrating thing that could ever happen. Was I wrong? So there seems to be this conservation of complexity. You know, Apollo, as I said, technically really complex, politically really simple. So you move into shuttle, all right, the technical complexity goes down, the political complexity goes up. And I'm going to extrapolate to space station, all right? Take the ops out for just a second. That's a big challenge, but development. There's not a hell of a lot of development in the space station program that has to, you know, new technology. We didn't really advance any technology in the space station program. But the political complexity was huge. I had the honor of being the first program director on the space station, and we sold it to the Reagan White House, and we sold it to Congress, and we had this simple thing, and we had all of our international partners there, and that was a way. We also helped keep it sold. We had a commitment, okay? You guys around the table here, to your countries, we committed to do this, and so we signed all the deals in the State Department. That helped the political, it kind of stabilized the political environment. But it was hugely complex, you know, from stability. The management changed, the configuration changed, the operations changed, the partners changed, so that's been a continuous thing. So think about that as you go forward into Constellation or whatever, okay? That see how it has evolved, and you're just going to have to know that that's a part of life, and you're just going to have to deal with it. The early formulation, let me talk about some of the things that we did in the shuttle to get to where we did. Our requirements in the shuttle, we had to have an Earth-to-orbit transportation system. We knew we had multi-year budgets that we had to look at and consider how to That means, do we front load this thing and do a lot of development at the front, or do we have a flat line budget? Well, that doesn't work very well, so there's got to be a peak in it, but it depends on whether you put your focus on development or ops. And then we had to look at those development ops costs. We had all kinds of masses and sizes of payloads we had to deliver, different types of orbital objectives and missions. We looked at a fully reusable system, turnaround time was it, and cross range. So what did we do? We said, so we started actually in 69, but there's a 1970 version. We said, okay, this is going to be a reusable system. Let's look at fully reusable, a reusable booster and a reusable second stage. But we didn't have much cross range on it. So that was one solution. We were doing about a configuration a day, literally looking at these things, studying them at a very high level parametric way. And we finally decided in about 72 that this is what the, see if I can hit this without back. This is the configuration as you see it today, almost, okay, not quite. But that was the baseline configuration which we began the DD-TNE in 72. So we studied in phase A and B, when you define a program, it's kind of a rule of thumb that's worked very well in the past. If you spend about 3% of what you think the program is going to cost on defining it, that's about the right magnitude. That's what we did on shuttle, that's what we did on space station, and then you know you've got something that you can accomplish. Yeah, there are a lot of hiccups that you're going to have to encounter, but that'll come about. And then we had to balance between the development and operations cost. And that was the big ditty. So we had to throw away the tank, because we couldn't do that fully reusable system. Just the money wasn't there. The thing is, we did not change the configuration. Shuttle didn't change the configuration. Apollo didn't. Shuttle and the orbiter, which I spent a lot of my life on, we started off with a $5 billion program. We developed the vehicle for $5 billion, exactly what we said. But bless his heart, Aaron Cohen, he just died in January. My mentor, he could do one thing. He could do a lot of things, but one thing he did very, very, very well is he said no. He would not change that vehicle for anything. The astronauts would meet with him about once a week at 7 o'clock in the morning. They'd get in before everybody else. They want to change this and want to change that. And Aaron would always say, no, no, no. There was one change that was made other than make work changes. I mean, we changed valves and fittings and tube structure things, things you had to make it work. But we didn't change the architecture, didn't change the overall design. We put a heads-up display in it. That was the only thing in that vehicle that changed. Dennis, don't think of something else that we did. Dennis has written the history of this thing, so he said wrong, no, but that was it. So if you can hold to that, if you do that foundation of planning, then you can make it work. And then the other thing was, as part of the change, better was the enemy of good. And I'll tell you a few examples of what we did. We made some changes and they bit us right in the butt. So we said, okay, we're going to hold the configuration, but in about 70, 75 or something like that, we had to make some changes, but we changed the program content. Let me give you an example. When we started the program, there was a full thermal vacuum test of the forward fuselage of the orbiter. I mean, all systems in it. Crew module, all the avionics, everything else. We're going to do a thermal vacuum test. Same thing on the aft end. We had a full thermal vacuum test. All the propulsion system and everything else was going to be there. What we did was we said, we're going to have to eliminate those things. But we eliminated them very, very carefully. We knew we could accomplish the mission. We would have to gracefully grow into it by not having those full thermal vacuum tests. We convinced ourselves we could do it analytically, but we had to start flying the missions very benign, as benign thermally as we could. We had 2 full orbiter airframes. That's on a 747, L-1011, those kinds of aircraft at the time. They always have a dedicated static test article and a fatigue test article. We started the program with a fully dedicated 2 airframes for static and fatigue tests. We ended up with none, okay? We tested the Challenger airframe. That was a vehicle, came off the assembly line. We took it, we tested it to 120% of mechanical loads. We pre-predicted every single strain gauge on that vehicle, 3,000 strain gauges. We said, as we start loading it, this is the way it's going to respond. And if we can do that, then we understand what we have. So lo and behold, we got it there. We put a pretty good load on it, 120% load, analytical mechanically. We combined the thermal stress with it, which was not insignificant. We said we're ready to fly. So that saved $100 million in the program, which we got $100 million cut that year. We said we got to save $100 million. So we scratched our head and said, okay, we think we can do that. So there was our test article. Crew module is not in this part. Loading jacks went in that. We pull this off, stuck the crew module in there, and put some tiles on it and flew it. That's oversimplified. But that was the Challenger airframe, and we saved that amount. Now, we didn't do that easily. The administrator says, oops, I don't trust you guys. So we had all these outside guys come in and grade our paper, and they said, well, these guys, we think they know what they're doing. On the simplifying the interfaces, there was, as we began the development of the shuttle, at JSC, Marshall had the responsibility of the payloads, and we said, okay, tell us what payloads to put in this sucker. Now, this was in 1972. They didn't have any idea, you know? So we said, they don't know, we don't know. So what we did is we looked at all kinds of variations in payload configurations, from mass, multiple payloads, CGF, CG forward, everything you can do. We had 10 million combinations of things. We did a Monte Carlo. We designed the mid-fuselage in '73 to exact that Monte Carlo thing. We didn't know where it was going to go, so we put sliding bridges in the vehicle to accommodate that flexibility. So what we did, we decoupled the orbiter design from the payload design. We also put a statically determinate system in there for you non-structural guys. That means it didn't matter what the stiffness of the orbiter was compared to the stiffness of payload. If you couple them too much, then you have to do an integrated loads. And we said, we can't do that, okay? So we simplified that interface. In the crew cabin, we had it float. It's attached at hard points. It's a pressure vessel sitting inside the forward fuselage of the orbiter. We did that so we could separate the loading in that cabin, so it was done, it's designed for nothing except pressure and a little bit of inertia loads. We want to keep that simple because that was a highly critical area. That was, I'll skip through that. That's the way that the crew module is attached at hard points here, here, around on the other side, and one down here. So you put it in, bolt it in, and so it's almost an autonomous piece of structure. Simplified interfaces. It let us proceed in parallel. Now then, we screwed up here though. The thermal protection system is bonded directly to, the tiles are bonded directly to the skin of the orbiter. Not a simple interface. As a matter of fact, when you look at a tile to show you the complexity we got into, you know, as the structure deflects, 90 thousandths of an inch deflection underneath that tile, you lose the tile. You lose one of 25,000 critical tiles, you lose the vehicle. So it was a hell of a challenge, and this was the pacing atom in getting the vehicle flying. We had 25,000 of these little suckers to say, yeah, we know we're okay to fly. Well, we got there. So our simple interfaces was the orbiter to ET. That again, we let the ET do its thing. We didn't have the two vehicles interacting, and then I've already mentioned the payload and the crew module and the TPS to the tiles. Early operations. We had to do a lot of things. In the first flight of the shuttle, and so in '81. There were two things that were a surprise. And one of the things that was a surprise was, because we couldn't simulate it in wind tunnels, going uphill, the pressure was on the wing was further aft and outboard. That changed the loading of the wing. We didn't design to that. So what we had to do was we had to placard all of the flights until we made that structural mod to stay within a capability. So we did that, okay? We placarded it, we learned how to do it, and the development guys think they've got it done, and whoever your development people are, they think they've got it fixed. But the ops guys save their ass a lot of times, let me tell you. And because there are things that the ops guys can do in conjunction with the development guys to make things work. You've seen it on Space Station, you've seen it. It'll be on every single program. You got to have that flexibility of accommodating things that you don't expect. Here was that I said we tried to not ever change anything, and when we did, it usually bit us. It was on STS-4, I think, maybe 3. No, STS-2, I've got it right there. We had a clog as part of the fuel cell system. We got debris in the line. We had to shut down one of the 3 fuel cells. We completed the mission. So we got back on the ground and we said, okay, we know what to do. We'll put a filter in there. We keep that material from going down and clogging the line. Well, 1 filter is good and that would do it, but 2 filters is obviously better, okay? So if you put 2 filters in, now you really got a good system. Wrong. Because what we did, we trapped hydrogen gas between those 2 filters. We collected the hydrogen gas in the tank, in the ullage tank. We could have blown up the vehicle like that. So, you know, if you have something that works, stop, okay? You don't have to keep going. So this was one of the examples of just better's enemy of good, and that was the placard we had in the project office. Better's enemy of good, and it paid off. A different thing in between Apollo and shuttle, and they extrapolate to space station, is spares. Not a very sexy thing, but critically important. The shuttle was up and flying, and the reason it was is we had to, as I said earlier, in '78, once we got, you know, a lot of momentum to go get that sucker in space, we kind of pushed aside some of this other stuff, and that was a detriment to the program, and it cost us some things early in shuttle operation. We didn't have and Russ knows more about this than I do, we didn't have the spares that we needed at the Cape, but we conscientiously knew we could get by, and then that got fixed. So don't ignore this. It's big. In the space station program, I woke up one morning early, you know, like about 1988, 89, something like that, and I said, my God, this is the biggest problem we got, the logistics, the reliability, all of the abilities, the supportability, the availability. And we didn't, at NASA, we didn't know that jargon. We had, you know, gotten there kind of in shuttle. So I went out and hired some guys from the Army, the logisticians, you know, come help us figure out how to do this thing, because it's going to be a hard thing. What I tried to do, and I don't know if it's still in the program or not, we tried to say we wanted that space station to be available 90% of the time to do science, okay? And that's complex. When you stop and think, I don't care what black box you're designing, you have to think about, is that black box going to work for the entire life of the space station program? Well, probably not. Well, if it's not, then you have to have some spares. Well, where are you going to put the spares? You're going to put them in space, or you're going to keep them on the ground. You're going to put them on the ground, you got to have a vehicle to take them up there. You got to train the crew to change the stuff out. So every black box has got to be systems engineered, if you will. And that's going to really be true if you have something on the moon or Mars. You better figure out how each little component is going to be available to do its job. You can design the life into it, or you can modify it, you can maintain it, you can spare it, but you better figure it out at the very beginning, or else you'll get to where you want to go, but you're not going to have, it's not going to accomplish what you want to. A big challenge, I think, for us. And the last thing I'd say is get a successful team. This, I said it was a real honor and a privilege in going through all the phases of the shuttle program, and it was another asset. Let me put it in that term. We never changed the team. That team stayed in place the entire time, from John Yardley all the way down to a grunt like myself, okay? We stayed, we kept the same guys in there. So Alan Lovelace, he said, what I'm going to do, shortly before the flight, he was concerned that we weren't going to get there and we weren't committed enough. So he said, I want you guys to tell me that you're committed to get this vehicle flying. So he said, let me tell you a story. He said, you know, to have a good breakfast, the pig really has to commit. Chicken kind of participates, you know, but the pig commits. And I want you guys to tell me you're committed to do it. So we said, yay, verily, we're committed. So he formed a Ham and Egg Society. It still exists. You know, a lot of the guys that you see up there are not there anymore. So hopefully on the last shuttle flight, we'll have a reunion. This was after the STS-1. We all met, we had a meeting down here, okay? And so we met, so hopefully we can do that again for our team on the last shuttle flight and come down and stand on the beach and watch it go. So let me stop there. We'll take some questions and answers, but I've met my schedule and now I'm going to turn it over to Rusty. No, to Jody. Yeah, excuse me. Yeah, I got that wrong. Okay. Jody, I don't know if, thanks.